as we continue our march here through formulas, what we want to be able to do is find the oxidation numbers that are on elements when they're bonded in compounds, whether ionic or covalent compounds. Now you'll notice that I've occasionally kind of interchanged these two words, oxidation numbers and charges. Well, what charges are on ions, if we have free ions. So if we have a hydrogen ion floating around in solution, its charge would be a plus. An oxidation number, however, is what kind of would be the charge if the structure split up and dissolved or was melted down, what free ions could be available, but they're not actually charged because they aren't actually available. So like H2O, hydrogen would still have a +1 oxidation number in that compound, but it can't really say it has a +1 charge because it's not charged, it's within a compound. So when we try to find what our oxidation numbers are, we have a set of rules, and these rules are a little bit messy, but I think most of these we probably already know. So step 1, rule number 1, is the oxidation number of any pure element is always 0. So if we have oxygen gas, O2, the oxidation number of oxygen within itself, bonding to itself, is 0. So there's no oxidation number, no potential charge on that compound. Same things if we have gold. Gold as a metal, just solid piece of gold, oxidation number 0. Any element you want to think of. You like tungsten? Throw out tungsten. Tungsten also has an oxidation number of 0. Okay, so any element by itself, neutral, pure, 0. Rule number 2, the oxidation numbers of all the atoms in a molecule must add up to 0. So when we add them all up, our compound cannot be charged. So that's a classic example of where we look at sodium and we look at chlorine bonded together, and whatever their ionic charges, now we know that the oxidation number of sodium is +1 because it's in the first column. The oxidation number of chlorine is -1 because it's in the 7th column, but notice +1, -1 add up to a total of 0. So overall the compound has to have no charge. So that's true with our little compound like sodium chloride, but it's also true if we have some big, more complex compound like PbC2H3O24. Well, everything within that compound has to add up to 0, whatever the individual charges might be. Same can be said for ions. The oxidation numbers of atoms within an ion have to add up to whatever the charge on that ion is. So if we are looking at phosphate, PO4 -3, well, whatever the charges are on the phosphorus and the oxygen have to add up to that -3 charge. So those are kind of all of our basics. Now, there's some oxidation numbers that we just know because, again, of their placement on the periodic table. So alkali metals always have an oxidation number of +1. We can always rely on that. Alkaline earth metals always have an oxidation of +2. And then oxygen nearly always has an oxidation number of -2. And the reason we're talking about oxygen is because oxygen's in a lot of polyatomic ions, in a lot of compounds, so oxygen is a nice reference to have. Now, occasionally we'll see hydrogen as a peroxide, as in or oxygen as a peroxide, as in hydrogen peroxide, or we can have sodium peroxide, where we see it as O2 bonded to something. Now that's possible, and then it has a -1, but again, like it says, that's in rare instances, and we will know that that is an exception when we run into it. So the thing we have to be careful of is these are true. These are always +1 and +2. And oxygen's primarily -2, but all of these things that we've said about that we can predict their charges based on their placement in the periodic table, well, that does work most of the time. The problem is when we get into things like our polyatomic ions, where we have maybe chlorine bonded to oxygen, and that's bonded to like a magnesium. Now we get a polyatomic ion where we have two things that are very electronegative bonded to each other in a polyatomic ion where they're both fighting for those electrons, so they both can't be negative. So this is a more accurate representation of the possible oxidation states of our elements, and notice it's a lot messier than what we said when we said +1, +2, +3. You know, that's all really nice and good, but it's not completely accurate. Notice our alkali earth metals hold pretty true to that rule. Notice boron, aluminum, gallium, indium, they all are holding pretty true. Carbon's primarily +4. Silicon, but they can also be -4, germanium, tin, now it can be +4, +2, lead can be +4, +2, so you can see that our pattern is starting to fall apart. And when we get into our nonmetals, look at all the various oxidation states of nitrogen. It can be a -3, which is its most common, but also can be +5, +4, +3. Now, when are we going to have oxidation states like that for nitrogen? Well, when it's bonded to things like oxygen, things that are more electronegative, so it can't be the negative element. Oxygen's more electronegative, so it's going to take the elements, it's going to make nitrogen become a positive, or have positive oxidation number. Other ones we have to be really careful of is look at chlorine, look at sulfur. These things have lots of variability. Again, most of that variability involves bonding to oxygen in various degrees. So they have different oxidation states depending on how much they're bonded to oxygen. Because oxygen is more electronegative, it pulls the electrons away, leaves them with a different oxidation number. So we had a nice pattern of 1 + 1, 2, 3, plus or minus 4, -3, -2, -1. And you notice that holds up primarily, but there's sometimes we have to be careful. And also, obviously, with our transition metals, which we already know, they have a lot of variability in their oxidation states. Except, actually, we should clarify, some don't. There's things like zinc, that's always a +2. Silver is always a +1. Those, we also should memorize that. They are always only those oxidation states. So let's go through and just try some examples. That's what we have to do. So notice they give some additional rules here. They say pretend hydrogen's always +1, which primarily it is, unless it's hydride. Oxygen almost always -2. Column 1's always +1. Column 2, our alkali earth metals always +2. And notice they're saying cyanide is a -1. So if we look at our examples here, our first example is MnO2. So they found the oxidation state on manganese. How did they do that? Well, they said we have MnO2, and our rule is, again, it always has to be a neutral compound. If it's a neutral compound, all the charges have to end up being neutral. We know oxygen's almost always a -2. Well, if there's 2 -2s, that's a total of -4. So the charge of manganese, or the oxidation number on manganese, has to balance that out, so it has to be a +4. So that's where we're getting the +4 for manganese. In the next example now, we have the permanganate ion, where manganese is bonded to a different number of oxygens, and it has an overall -1 charge. Now the overall charges on these individual compounds have to add up to that -1. So oxygen's -2, -2 times 4 is a -8. Now, what plus -8 gives us this -1? Well, in this case, manganese, like it says, has to be +7. And don't worry about having a crazy oxidation number on manganese, because if we go back to that periodic table, look at manganese. It can have a ton of variability within its oxidation state. And notice it can have a +7 because it could lose 1, 2, 3, 4, 5, 6, 7 electrons. If it lost all of its d and s shell electrons, all of its outside electrons, it could lose 7. So even though it seems crazy, not crazy as it seems. I'm going to do some more here. We have sulfuric acid. Notice it's telling us obviously the answer, but let's see how that is derived. So H2SO4. Again, for a compound like this, we want to work off on the edges. We always want to, again, it's a neutral compound, but we also want to start with oxygen, because oxygen, it can be a peroxide, but again, that's kind of rare. So there's -2 times 4 is an overall -8 charge on our oxygen. Next, I'm going to slip over to hydrogen, because hydrogen is pretty commonly a +1. It's very rare that we're going to have a hydride. So it's +1 times 2 is a +2. So sulfur has to make up the difference between those to give us our neutral compound. If there's a +2 from our hydrogen, overall -8 being donated from our oxygen, sulfur has to be a +6 to even out to get our overall neutral charge. We'll just do 2 more here. So we have the chromate ion. Again, it has an overall -2 charge, so that's what we have to get to. Oxygen, again, is -2. We have an overall -8. So what plus a -8 gives us a -2. That means chromium has to be a +6. So +6, put it together with a -2, we get that overall -2 charge. Finally, I'll just do the dichromate here. A Cr2O7 with an overall -2. Again, oxygen is -2. Times 7 is -14. So what plus a -14 is going to give us a -2? Well, we have to have an overall +12. But here's where we want to be a little bit careful. Chromium is not a +12 because there's 2 of them. So we divide that charge onto each chromium. Each chromium is a +6. So we're interested again on the oxidation state of the individual element.